Why would I watch this video?
I don't know. Maybe you really
Kids actually do though.
really like physics. Really bad. I almost fell. I almost fell. The chair almost slipped up and then right there. Like slightly.
No, it goes like this every time. You see like middle edition on my backside. And like, what's your middle?
Henry, why are you asleep?
No, Lewis.
Should be. I don't care.
My medication makes me really sleepy. So I have been taking like literally 4 hours naps. I watched 2 movies yesterday. As soon as I forgot.
Fun first name.
I watched so much yesterday.
Right to be a senior.
My middle name.
I'm ready to be a senior.
Kind of stressful though. It's not on the subject. Yeah, I know. I'm just gonna like hold it now. With my hand.
Feel free to give them a
Low mileage for a car full of 70s could be anywhere from 30 to right here. You don't want yeah, but like you can go on with their money.
Yeah, I'm not.
Okay, sorry about that.
I was getting that.
All right, let me begin today with 2 demonstrations. Okay, first of all, just as another example of an interference pattern, what I'm going to do is pass around this stack of panes of glass, and when light from the ceiling enters the stack of panes of glass, at each individual boundary, the light reflects and it also refracts. So you basically end up with light from the ceiling splitting off into multiple paths. And then all of that light then interferes and produces a noticeable interference pattern. The way that you see the interference pattern is to hold a stack of glass like this and position it such that you see the reflection of the ceiling lights in the top pane. And then when you do, you'll see what appears to be a pattern of alternating bright and dark fringes that appear essentially as curves or rings. This is sometimes referred to as Newton's rings for this reason. Okay, the fringes themselves, you'll be able to see, are actually split up into their component colors. You're actually going to be able to see the Roy G. Biv. And then if you kind of shift it around as I'm doing it here, you can then see the pattern change. It's a little bit tricky to look at initially until you understand what it is that you're seeing. But you want to position it like so. Look at the top pane and position it such that the ceiling lights are reflecting off of the top pane, and then you'll be able to see the interference pattern. We'll just kind of slowly pass this through the room over the first portion of the period. So take a look when it eventually comes to you. Okay, however, before you're really going to have a chance to look at this, however, I do have to turn the lights off for my next demonstration, which is another version of Young's experiment. Okay, what I'll be passing around to just about every row here in just a few minutes is a light bulb that first of all has 2 colored pieces of paper on it. The red paper here basically allows red light through, but it blocks everything else. The blue paper here allows blue light through, but it blocks everything else. And then right here is one of these cards, similar to the one that I used last time in class to show you Young's experiment when it's cast here onto the board. When one of these cards comes to you, what you want to do first of all is in one of the corners there's a manufacturer's insignia. And then right below that insignia are a series of double slits. What you then do is hold the card, those double slits, right up to your eye like so, and then first look at the red light, and when you do, in the shape of the filament of the light bulb itself, going outwards from the filament, you'll see an alternating pattern of bright and dark fringes. Okay, then when you do the same thing with the blue light, you'll notice 2 things about it. Number one, it's a lot dimmer, so it's a little bit harder to see. And in addition to that, the fringes are all really close together, as opposed to the red, which is brighter and the fringes are far apart. It's easy to see. With the blue, it's a little bit trickier. And then lastly, turn the light bulb around, so you're just looking at the white light. And when you do, you're looking at the entire smear, if you will, of Roy G. Biv. And then do the same thing. hold the card up to your eye as I'm doing here, and then look at the alternating pattern of the bright and dark fringes. When we look at the demonstration in this manner, by the way, where is the screen?
Your eye.
It's the back of your eyeball. The fringes actually form on your retina. Now I'm going to pass around a couple of light bulbs and a couple of these cards per row. We'll turn the lights off so you have a chance to look at it. Let me do this first of all on this side of the room. 1, 2, 3, 4. So let me use these cards that I have in my hand. So careful, please. Plug it in. I'll do, yeah, go ahead and plug it in. I'll do the same thing here on the other side. 1, 2, 3, 4. So I'm dropping these light bulbs all over the place. Henry, stay with me. There you go. So, okay, then let me give you guys a couple of cards here per row. Once again, when the card comes to you, you want to locate the manufacturer's insignia. Let me give you guys another one here. See, it's a small class. I could probably give you 2 per row here on each side.
So Mr. Schauer, when you wear polarized sunglasses, how come you can see the color of the bottom?
Polarization is another effect of light as well. It is well contained within our study here of optics. But basically what light polarized lenses do is it lets light of a specific direction through. Okay, now, I'm going to turn the lights off here so you can see this. And incidentally, while you're waiting for the cards and the light bulbs to come to you, especially when you're in the middle desk, you can actually also see the interference pattern another way by doing this just yourselves. What you'll do is take the white light, for example, and then stare at the light bulb as I'm doing and then squint, like so. Because if you do this while you're squinting, you're actually going to see even the Roy G. Biv of the alternating pattern of light and dark fringes going outwards from the bulb itself. So take a look at it. So where are the slits then if you're doing it like this while squinting?
Your eyelashes.
That's right. Your eyelashes form multiple slits, thereby producing a similar interference pattern. So interference patterns associated with light are actually noticeable under the right conditions, but you really got to look for them. So if you've ever noticed how you may have seen the Roy G. Biv of colors by squinting before when looking at light, this is an easy way of seeing it. So just squint at one of the light bulbs and you'll see going outwards from it the alternating pattern of Roy G. Biv. So everybody take a look at these different effects when the card comes to you and also when the bulb comes to you. When the card comes to you, by the way, you want to position it so the slits are like this. Not like this. Position it so the slits are like this. Okay, while you're waiting or after you have seen it, let's go ahead and begin to copy down the following problem, which corresponds to this demonstration. This is
What are you doing?
yes, go ahead, Zach.
One more time, we're able to see the Roy G. Biv when you look for the light.
Okay, so the reason why you see the Roy G. Biv when you use the card is because when you look at the white light, you're looking at a smear of interference patterns. You're looking at multiple interference patterns of the different colors, which then interfere together. That's basically what this problem here is all about. And incidentally, once everybody in the row has had a chance to see all of this, please then bring the light bulbs and the cards back up to my desk if you would please. Once everybody's had a chance to look in a row, bring the light bulbs and the cards. If you don't mind, please back up to my desk. Once you do, I'll turn all the lights on and I'll open the door. Okay, so once everybody in the row is seated, bring the light bulbs and the cards, please, back to my desk. Thank you very much.
Is that what we're supposed to do? One person? I'll do it. You guys. And please not that.
Oh. Yeah, I got that part, but then I wasn't sure that.
So you have to hold the card up to your eye. It has to be directly against your eye, basically. Such the screen is then your retina, which is being described here as an example. So once again, last couple of bulbs. Once you guys have had a chance to look, please bring everything back up to my desk, please. Thank you.
I've been making hair box all day, so
Okay, now I'm going to go ahead and turn the lights back on so you can continue to look at that interference pattern in the stack of the panes of glass as we slowly pass that through the room.
I just want eternal silver.
Okay, now this particular example here explains why the patterns look the way they do. Why the red light pattern, for example, has all the fringes spread out from each other, as opposed to the blue light, which is a lot less noticeable, as you discovered. In the blue light situation, the fringes are a lot closer together. We'll see directly why here in this example. We'll also understand why that when you look at the Roy G. Biv of the white light, why it all just kind of smears together to produce a single interference pattern, or pretty close to it. How many of you were able to see the pattern by squinting through your eyelashes as well? Absolutely. Now don't hold it like that, Nash. Hold it like this and look at the top pane. And then position it such that the ceiling lights reflect off of the top pane. So you'll have to tilt it around a little bit to see that. And if you glance at it at an oblique angle, you should see an alternating pattern of bright and dark fringes that appear like colored rings.
Oh.
There you go. It's easy for me to tell when he sees it. Okay, so here's what's being described in the example. Remember the basic drawing, the basic setup that we have for Young's experiment? It looks like this. Where we now have the following distances here in this version of the problem. So small d, remember, is the slit separation. Okay, that's equal to 0.5 millimeters here once again in this example. Immediately we have to convert this, however, into meters. So, first of all, convert this into meters. It's 0.5 times 10 to the minus 3 meters, like so. Okay, and then the distance from the slits to the back of your eyeball, that's the screen here in this version of the demonstration. Remember, that's called L. Okay, this is given to us as 2.5 centimeters. That's about the diameter of your eyeball. We have to convert this into meters as well by dividing by 100. Okay, now we're looking at the n equals 1 bright fringes of both the blue and the red light that's described in this problem. So remember from last time what our bright fringe equation is. The path length difference, dy over L, is equal to n times lambda. We're specifically in this problem, however, we're given that n is equal to 1. Okay, now if n is equal to 1, this immediately explains why it is what we see. So if I set here the n equal to 1, like so, now think of it very simply in the following way. The L and the D here don't change in the example as we change from the blue light, which has a small wavelength, to the red light, which has a larger wavelength. So if we change the lambda, but nothing else, what then happens to the y? Well, it changes as well. So if you increase the wavelength of light from blue to red, then the value of y, which remember is a distance here along the screen, increases. So this immediately explains why you see the fringes of the red light as more separated from each other than the blue light, because the red light very simply has the longer wavelength. So then therefore it's going to be a pattern that's more spread out than that of the blue. So if we combine now just two colors of light together here for this example, basically opposite sides, if you will, of the Roy G. Biv portion of the spectrum, then here on your retina, essentially the pattern looks like this. We first of all have the central maximum of the blue, and it's right on top of the central maximum of the red, like so. But then on either side here, symmetrically, on either side of the central maximum, we have the n equals 1 bright fringes. We're going to see, however, the n equals 1 bright fringe for the blue first, because of the smaller wavelength of blue light, as opposed to that of the next red fringe, like so, that of the red light. So that's what the pattern would look like if we were just using two colors here at the same time. Okay, now we're looking at the n equals 1 bright fringes here for blue and red. Each one is some distance away from the central maximum. So for example, right here is a y blue, and then for the red one, right here is a y red. In order to calculate how far apart those two fringes are from each other, basically what we have to calculate is y red minus y blue. So I'm going to call this value here delta y. That's what we're asked to solve for in the problem. As we'll see, it's really tiny. Okay, now we've got our two colors of light. We have our two wavelengths. So we're given that lambda blue is 480 nanometers. Once again, we immediately have to convert this into meters. This is 480 times 10 to the minus 9 meters. So, okay, then we have our red light. We have lambda red. That's 630 nanometers. 630 times 10 to the minus 9 meters. Once again, we have to do that conversion. So just for reference, that's 630 nanometers. Okay, now basically what I have to do is just simply take my bright fringe equation right here, solve it for y, and then just write it in terms of the red minus the blue to get what it is that we're looking for. So I'm going to do a little bit of cross multiplying here with this green expression. I'm going to solve it for y by cross multiplying the L and the D to the other side. And when I do, I obtain the following. And now I just subtract one from the other with the respective wavelengths plugged in. So the difference then in the values of y here is going to be, first of all, y for the red minus then y for the blue. We can go a little bit further here with the math. I can factor out an L over D from each term to then therefore give me the following expression. And at this point, I just go ahead and plug in my numbers. Okay, when I do plug in my numbers, it's actually a little bit easier if you do the parentheses here first, which notice is just the difference between the wavelengths. So 630 minus 480 nanometers. This right here is 150 nanometers, which is 150 times 10 to the minus 9 meters. And now we just plug it in. So I'll do the parentheses here first. 150 times 10 to the minus 9. Multiply that by L, 0.025 meters, and then divide by small d, 0.5 times 10 to the minus 3 meters. And you end up with a really tiny distance. It's only 7.5 micrometers, so 7.5 times 10 to the minus 6 meters. In other words, two patterns here, basically on opposite sides of Roy G. Biv, are so close together that if you looked at them at the same time, they basically are almost right on top of each other. They would essentially interfere with each other. This is what you see then when you look at the white light. When you look at the white light, you see the alternating pattern of bright and dark fringes, but you probably notice that each bright fringe had a little bit of Roy G. Biv associated with it. That's because they're all at slightly different distances, but the difference between those distances, as you can see, is next to nothing. Now, when Thomas Young did the original experiment in 1801, he didn't use a laser of a single wavelength of light, like I demoed it for you last time in class. He used a candle. Okay, a candle shines brightest in the yellow portion of the Roy G. Biv, which is basically right in the middle of it. So you just saw the alternating pattern of bright and dark fringes, much like you saw with the white light with the filaments of the light bulb, but he did, of course, notice the Roy G. Biv, that everything was being smeared together. Okay, that's basically what I'm saying. All right, moving on from there, let me erase. And next we start moving towards an understanding of how mirrors work. Understanding how any mirror forms any type of an image, it all is based upon one simple relationship that is referred to as the law of reflection. The law of reflection is going to be our starting point for understanding mirrors, for example. And when we use the law of reflection, we now start to enter what is referred to as geometrical optics. The law of reflection is based upon Huygens principle. Now previously, back in our last unit on mechanical waves, I talked about Huygens principle, and I introduced you to the idea of using a little applet. We're going to look at that applet here once again. If you recall, I originally used it to describe water wave refraction. Now we're going to use it in a slightly different context. So from our last unit, here is that applet once again. And now, the way that we'll think of it here is that we'll think of the yellow as air, and then the boundary between the yellow and the blue, we'll think of this right here as a mirrored surface. And then right here is going to be our incident plane wave of light, which is then going to strike the surface. And now Huygens just basically assumes the following. He assumes that every point on the surface is a point source of circular wavelets, such that when the incident plane wave of light in the yellow hits those sources, circular wavelets then propagate outwards from those points to then constructively interfere to form a reflection, a reflected plane wave. Recall what this looks like when I set it into motion. Okay, now back in our last unit, we were talking about what was going on in here with the refraction. We'll get to that again eventually when talking about the refraction of light. But now what we're concerned with is describing the propagation of this reflected plane wave like so, which is now propagating in this direction due to the reflection of this incident plane wave. Now Huygens just assumes that this is happening. This is 200 years, however, before our understanding of electromagnetism. Huygens basically just assumes this and goes from there. If you make this assumption, it leads you to a very simple relationship that describes the geometry of the incident and reflected plane waves, called the law of reflection, which is then therefore the entire basis of understanding, for example, how mirrors work. All of this can be done by just using geometry. In other words, without knowing the underlying electromagnetism. That's why this is referred to as geometrical optics. The brilliance of Huygens' idea, however, is that this is really what happens. He actually guessed correctly, because what actually happens is the following. If you're talking about a mirrored surface of polished metal, the individual point sources, it turns out, are the valence electrons, the outermost electrons that are loosely bound to their atoms in a metal. And then when the incident electromagnetic wave strikes those individual electrons, each individual electron gives off a circular wavelet like so. They all then constructively interfere to produce a reflected plane wave. So he just made essentially an educated guess. He just assumed that this is what's happening. It turns out that he was exactly right. And he made this guess basically 200 years before we understood the nature of the electromagnetic force. Zach?
So if he was wrong, his whole life's work would...
No, not necessarily. If he was wrong, then frankly physics wouldn't work the way that we know that it does today. But he made essentially a brilliant guess. He made a brilliant guess based upon the wave-like behavior of light and already understanding how mechanical waves behave. Like, remember I showed you the point sources with the board that they had that all the nails were into it. If you just assume the same thing is happening with light, then it's actually very easy to explain how mirrors form images, how lenses form images when talking about refraction and so on. You reduce what is ultimately complicated electromagnetism, you reduce it to just pure geometry. That's why we refer to this as geometrical optics. So just kind of briefly summarizing that in a few sentences, Huygens basically assumes the following. Huygens assumes that when a plane wave of light strikes a mirrored surface, not source, but surface. Each point source, the individual electrons, it turns out, that are loosely bound to their atoms in the metal. Each point source emits a circular wavelet, resulting in a reflection, as we see in the applet. If you just, as I said, simply assume this happens, it leads us to a simple geometrical relationship. This assumption, we'll see in just a few minutes, leads to a simple geometrical relationship. hence the phrase geometrical optics. In order to understand geometrical optics, how mirrors form images, a little bit later on how lenses form images and so on, the underlying electromagnetism is completely unnecessary. Okay, so what is now this geometrical relationship? What is the law of reflection? Well, it's actually somewhat intuitively obvious, but showing how it works is a little tricky here initially. Now, in the context here of this applet, think of it in the following way. So right here we'll say is our mirrored surface. And then we have incident plane waves on the mirrored surface. In the applet, we just see one wave crest. Here it's necessary, however, to draw. So let's say that right here is an incident wave crest, and here's another incident wave crest like so, such that the distance between them is equal to the wavelength of the light lambda. We already know now that the wavelength corresponds to color. Okay, now the direction of propagation, if you recall, is perpendicular to the wave crests. That's this blue line right here like so that we've seen before. This is now referred to as the incident light ray. Okay, now notice that here on my diagram, just like you did when deriving Snell's law back in our last unit, we end up with a right triangle. And on the right triangle, right here is an angle. Like it was before, this is the angle of incidence. It's the angle that the plane waves make with respect to the mirrored surface. This right here is theta sub optima. Okay, now, through Huygens principle, as we see here in the applet, these two plane waves here and here reflect. So for example, this guy here has a reflection that looks like this. This guy here has a reflection that looks like this. The distance between the wave crests is once again equal to the wavelength. But remember in the applet here that these guys are propagating in this direction. So the reflected light ray is drawn like so. This right here is the reflected light ray. Where once again we form right here another right triangle. Right here is a right triangle associated with the reflected waves. Right here is the angle of reflection associated with those reflected plane waves. Right here is theta sub r. Okay, now if you look carefully here, there's just two right triangles. There's a right triangle right here for the incident wave, and there's a right triangle right here for the reflected waves. If you look at my diagram carefully, what could you say about those two triangles? That's right, they're congruent right triangles. I said the word geometry. I wasn't kidding. They're congruent right triangles. Okay, now how do I know that? Well, they're both right triangles like so. They share the same hypotenuse, and they also have the same side. Right here, for example, for the incident triangle, that side of the triangle is the wavelength lambda. Right over here for the reflected triangle, this side of the triangle is the same wavelength lambda. So then therefore they're congruent right triangles. If they're congruent right triangles, what could you say about theta incident and theta reflected? They're the same. That's the law of reflection. The incident angle is equal to the reflected angle. This is our starting off point for understanding anything associated with mirrors. But when it comes to tracing out how images are formed by mirrors, we don't draw anything nearly as complicated as this. We simplify the diagram considerably. Here's how we simplify it. Instead of drawing all the individual wave crests and so on, frankly, we don't even bother. Instead, what we just draw are the light rays, the incident and the reflected light rays, and we draw them in the following way. So right here is once again my mirrored surface. And now let's just take a look at right here, my incident light ray coming in like so. Okay, now right here at this point where the light ray hits the mirror, draw a dotted line that is perpendicular to the mirror at that location. This is referred to as the normal line because if you recall in mathematical lingo, the word normal means perpendicular. Okay, now over here on this diagram, if this right here is my incident light ray, the normal line is the marker right here like so. If you futz around with the geometry appropriately, you can show that this angle here that is made by the marker is the same thing as the angle of incidence. That is, on this diagram, this right here is the angle of incidence. Okay, then I've got my reflected light ray, now drawn like so. So if that's my reflected light ray, over here on this diagram, here's the reflected ray like so. The marker here is my normal line, perpendicular to the surface. Once again, if you futz around with the geometry, you can show that this angle that is made right here by the marker is the same thing as the angle of reflection. So right here is the angle of reflection, and the two angles are equal to each other. That's the law of reflection. So we don't draw anything nearly as complicated. We just draw the light rays reflecting like this. Now it's important to realize that the two angles are equal to each other. They don't necessarily add up to 90 degrees. They're not necessarily complements of each other. So in other words, if this is 5 degrees, this is 5 degrees. If this is 10 degrees, this is 10 degrees, and so on. So they're equal to each other. They are not complements. And now in just a few minutes, after we take our short break, we're going to go through a discussion here of exactly how mirrors form images. There are three basic types of mirrors. The first type is the easiest type, and that is what is called a plane mirror. That's where the mirrored surface is completely flat. Before we get to all that, however, during the break, I have a nice little demo here for you to take a look at, because I'm going to refer to this demo as a problem in just a little while. What I'm going to do is take two mirrors and form a mirror combination. If you take two plane mirrors and face them parallel to each other like so, you form a mirror combination that is called the barbershop mirror combination. How many of you have ever been in a room where you have two mirrors on opposite sides of the wall? And then what do you see when you look in those mirrors? Yeah, you see an infinite number of images which kind of gray out and fade as you get further and further away, apparently, from the mirrors themselves. We'll explain why that happens the way it does in just a little while, but for now, I invite you to come up here and take a look at it. Because what you do is look in this little hole right here, like so, to see the infinite number of images receding in this manner. So while we're taking a break, come on up and take a look. We're reintroducing it here again, because now we're going to speak very further. So if you want to take a look at it again, or do something. No, we don't.
I'll be out of it.
Why is everybody so tired? APs, I know it's coming up.
So many finals this week.
By the way, I have something to say about AP tests coming in the next couple of weeks. I'll be saying a little bit more about it next time.
It was physics.
Well, because it's not AP class. This class doesn't stop. I'll tell you about my policy about AP class.
I don't.
Did everybody get a chance to look at the stack of the panes of glass?
Yes.
All right, everybody, stay with me. I know it's a tough time of year.
So
Stay with
I
me.
got final today and.
Did you have the, you already had the test?
Yeah.
Well, we have the multiple choice to
Well,
tomorrow.
that's okay, at least it's over now.
Right, half of it is over. What?
It wasn't hard. Oh, AP Gov sucked.
But
AP Gov sucks, don't take it.
but it wasn't like the tests are.
Okay, now we get to mirrors. Geometrical optics, frankly, is easy. It's just geometry. You have to follow along carefully, initially, it's a little tricky. By the way, I know that a lot of students that enroll in this class, honors physics, are maybe thinking about medical school, for example, sometime in the future. You would not believe how much optics appears on the MCAT. Do you guys know what the MCAT is?
Yeah.
Medical practice, that's the exam that you have to take in order to get into medical school. There's a huge amount of optics that is included on the MCAT.
Why is
That's one of the reasons why it's on the MCAT is because of the physiology, for example, of your eye. In addition to that, we use various versions of optics, not using visible light, but using other types of waves to look inside the body with magnetic resonance imaging and so on. So the biophysics that you would need, for example, some of it starts here, which is understanding how mirrors and lenses work, which is what we're going to start moving towards. Okay, now when it comes to mirrors, there's three basic types. There's the plane mirror, which as you'll see is pretty straightforward. There is also what is called a concave mirror. That's where the mirrored surface is on the inside of the curvature, like that one over there that you saw last time in class, and the convex mirror. In a convex mirror, the mirror surface is on the outside of the curvature. Okay, we begin our discussion. Shruti, stay with me, with the plane mirror. First thing that we want to understand is how do you construct the image? Okay, now we begin to diagram out the situation in the following way. Okay, we're going to say that the mirror is here on this wall, and then let's say that here is the ground. Let's just assume that the mirrored surface here is on the left-hand side. And then we have an object that is standing in front of the mirror. We always represent the object, by the way, as an arrow because it shows direction. It shows orientation. So imagine that we have an arrow here that is standing in front of the mirror, like so. So let's say you just stand in front of a bathroom mirror in the morning, the lights are on, so there's light reflecting off of you. If you think about this carefully, how many light rays are reflecting off of your body when you stand in front of the mirror? More than several, an infinite amount. So how many light rays do you need to construct the image? You only need 2, but you have to use 2 light rays here carefully. What I'm going to do is take 2 light rays that are coming off the tip of the arrow and then striking the mirror. What each light ray does, it simply undergoes the law of reflection. So for example, take a light ray, have it go from the top of the mirror, or excuse me, the top of the arrow, and strike the mirror here on the right-hand side of my diagram. Now right here at this location, right there is my dotted line that is perpendicular to the surface. So right here is my angle of incidence. And then therefore, I simply reflect this light ray at the exact same angle. That then looks like this. Like so. So right here, also in green, is the angle of reflection. Okay, now I just do the same thing arbitrarily with a second light ray. Take a second light ray that goes from the tip of the arrow and have it say strike the mirror like this. So then right there at that location on the right-hand side of my diagram, right here is my dotted line that is perpendicular to the surface. So right here then is my angle of incidence. Notice that it's a bigger angle than this original angle of incidence right here. And now when I reflect that light ray, all that I simply do is reflect it at the exact same angle. So that then gives us a reflection that looks like this. So right here, the angle of reflection. Now take a look at the 2 reflected light rays. Here, here. Notice that they're splitting apart from each other. They are diverging, as we say. We have diverging light rays. So then therefore, if those light rays entered your eye, for example, just a picture, let's say your eye right here. If those light rays entered your eye, where did they look like they're coming from? Well, they look like they're coming from some point behind the mirror. Why? So watch what happens if I take these 2 reflections and extend them back behind the mirror. Like so. Like so. Notice that they come together behind the mirror. That is then where you would see the image of the tip of the arrow. The image of the tip of the arrow forms here. And then if you did this process for all points on the arrow itself, you would then form its image right here. Now, if you think about it, this is not all that surprising. Because if you stand in front of a bathroom mirror and wave at yourself, where does it look like your reflection is waving from? In other words, does it look like it's at the mirrored surface, in front of the mirror, or does it look like that the reflection is behind the mirror? It looks like it's behind the mirror. This type of an image is referred to as a virtual image. Now, as I was describing this, somebody said, why does this work the way it does? The reason why this works the way it does is because these reflections here and here are diverging. They're coming apart from each other. So then, therefore, it looks like they're coming from the same point behind the mirror. That is then, in other words, where your eyes are focused upon. That's then where you see the image of the tip of the arrow. And then if you did this process for all points along the arrow itself, you would then see its image back here. Now there's a very simple relationship that describes where the arrow is, that is its image, in relation to where the object is. In order to describe that relationship, let me define 2 distances. Okay, first of all, this distance here that the object is in front of the mirror is just simply called the object distance, and this is labeled as DO. And then, over on the other side, this distance right here is how far the image appears from the mirror. This is referred to as the image distance. It's called DI. Even though my diagram is perhaps a little bit off, it's actually pretty obvious what the relationship between DO and DI is. Here's how you show that relationship. What I'm going to do is construct 2 right triangles. So there's a right triangle here on the left, and there's a right triangle here on the right. Notice that those 2 right triangles, here on the left and here on the right, first of all, share the same side. so. And now, take a look at this little tiny green angle of reflection right here. What could you say about that little green angle of reflection right there and this angle right here? They're the same. Does anybody remember what that relationship from geometry is called?
Yeah,
Where this angle here is equal to this angle? Anybody remember what that's called?
Oh, it's like.
Who cares? The angles are equal to each other. Good enough. Okay, now, let's take a look at this blue angle here and this blue angle here. Okay, first of all, on the left-hand side, this blue angle here, the complement of this initial angle of incidence. This blue angle here is the complement of this green angle. However, we already know that this angle of reflection is the same as this green angle here, which is the same as the angle of incidence. So then therefore, what can I say about the blue angles?
The same.
They're the same. So then therefore, because I have two right triangles which share the same side, and they have the same angle, what can I say about the two triangles left and right? They're congruent. So if they're congruent right triangles, what can I say about DO and DI?
Equal.
Is everything?
Once again, this shouldn't be all that surprising. You stand 5 feet in front of a mirror, for example, you wave at yourself, where does it look like that your image is? It looks like it's 5 feet behind the mirror. Let's take a look at a basic problem involving let's understand why bathroom mirrors are hung on the wall the way they are. Let's say that we have a 6 foot tall person standing in front of a mirror. The person wants to be able to see his or her entire image in the mirror. Let's also assume that the person's eyes are 4 inches below the top of the person's head. In order for the person to see their entire image in the mirror itself at least has to be a certain size. That's one of the things we have to find. And it also has to be positioned somehow a certain distance above the floor. That's the other thing that we're going to find here in this problem. Now, how do you begin to think of this problem here? Well, I'm going to kind of draw it out in the following way. Once again, we'll think of the mirror on the wall on the left-hand side of that vertical line, and then the person I'll represent as an arrow. I'm going to draw the arrow rather large here in this example, however. Let's say right here is the person. The person has a total height here, h is equal to 6 feet. And then the person's eyes will say right here. We're given that the distance that the person's eyes are below the top of their head is 4 inches. 4 inches, by the way, is 1/3 of a foot. And this distance right here is that distance. I'll just call it A. The distance A here is equal to 1/3 of a foot. That's 4 inches. Okay, now, at the following, the very least has to happen. For example, imagine a light ray coming off the bottom of the person's foot, and at the very least, striking the bottom of the mirror, undergoing the law of reflection, and then reflecting back into the person's eye. So at the very least, the following has to happen. The light ray comes off, strikes the bottom of the mirror, reflects then into the person's eye, like so. So at the very least, the bottom of the mirror has to be here. Okay, now, here's the geometry. Here's my dotted line that is perpendicular to the surface of that location. And what I actually end up with here is, once again, a set of congruent triangles. Okay, this distance here will be important in the problem in just a few minutes. Let's give this a name. Let's just call this B. Okay, now in addition to that, at the very least, the following also has to happen. Imagine, for example, a light ray coming off the top of the person's head, striking on the top of the mirror, undergoing a law of reflection, and then reflecting back into the person's eye. So just as I pantomimed a moment ago, at the very least, the following has to happen. Light ray hits the top of the mirror, reflects into the person's eye, like so. So at the very least, the top of the mirror has to be here. Now once again, there's some geometry here. Right here at this point, this dotted line here is our normal line like so. And then I once again end up with another set of congruent right triangles, here and here. So here's then what we're asked to find in the problem. Number one, the size of the mirror. And then number two, how far above the ground the mirror is. Now if you just kind of stare at my distances here on the diagram, what is the size of the mirror? Can you tell me?
Yes.
Not numerically, but just in terms of the variables I wrote down here. What is the size of the mirror?
A plus B.
It's not A plus B. Well, it's
Half of
this plus
B,
this.
half of B
Half of A.
plus minus half of A.
No, it's half of A
Plus
plus
half
half
of
of
B.
B.
So you're right, you said that.
So notice that the size of the mirror
Plus. Right.
is equal to A over 2 plus B over 2. Okay, now, how do we find that number? Well, we know that the height h on my diagram, 6 feet, is A plus B. So then therefore, just divided by 2. So the size of the mirror is h over 2, therefore it's 3 feet. So if you have a 6 foot tall person, at the very least, the mirror has to be half of their height. So when you look at ordinary bathroom mirrors hanging on the wall, you'll probably notice that, roughly speaking, they're about half the size of a typical person. However, you also have to position the bottom of the mirror here a certain distance above the floor in order to ensure that the person is going to be able to see their feet. Okay, just looking at my diagram, what is that distance, Nick?
Sorry.
Okay, go ahead, your question.
Even if the mirror is just like 2 inches in front of you, you'll still be able to see the...
Yeah, I haven't said it yet, but notice what is not important in this problem.
Distance.
It doesn't matter how far you are from the mirror. That's not even entering into the problem. But let's do the last portion of the problem before I explain that portion of it here once again. So looking at my diagram here, what is the distance that describes where the bottom of the mirror is in relation to the floor? What is it?
Half of B.
Yeah, that's right, it's half of B. So let me do that here in the bottom board. The distance that the mirror is above the floor is B over 2. Now how do I find that? Well, I'm going to find that from this little expression right here. I'm just going to solve this expression for B over 2. So move the A over 2 to the other side. So B over 2 is H over 2 minus A over 2, like so. Remember that H over 2 is 3 feet. And then this right here is just minus 1/3 of a foot divided by 2, which is 1/6 of a foot. So this is 3 minus 1/6, which is 2 5/6 feet. So that's pretty low to the ground. You would have to take a mirror that's half the size of the person. You have to kind of position it so that the bottom half, the bottom portion of the mirror is right about here to ensure that you can see your entire body, that is, see the entire image. And this doesn't matter. It doesn't matter how far you are from the mirror, which is somewhat counterintuitive. Now here's a way in which you can sort of see this for yourself. Okay, no, when you go into a bathroom here at school, you're not going to see the mirror positioned this low to the ground. It's going to be mounted up higher on the wall. So then therefore, you're probably not going to be able to see your feet. Instead, it will cut off, say, around your waist. So you'll be able to see from the waist all the way to the top of your head with a typical bathroom mirror. If you stand far from the mirror, you'll see just from the waist up. If you get close to the mirror, you'll see just from the waist up. Once again, the distance DO here, somewhat counterintuitively, doesn't matter. Okay? So that's why bathroom mirrors are hung the way they are, and why they look the way they do. Okay. Next. I'm sorry?
Will the mirror size usually be around?
Well, if you look at a typical large bathroom mirror like we have here at school,
Yeah.
okay, the height of that mirror is roughly half the height of a typical person, and it's positioned, 4 or 5 feet above, 4.5 feet or say, something like that above the ground.
Right.
So then therefore you're basically gonna see from the waist up, and it doesn't matter how far you're standing from the mirror.
So even if you're standing 15 feet away,
Yeah, you're still gonna see waist up. You stand like right up against it and kind of look like this, you're still gonna see waist up. Yeah, try it for yourself. No, we're not gonna take a field trip. No, I'd have to have everybody fill out permission slips and all the rest of it. We'd have to order buses. All right.
wait for David Ryan.
Okay, let's take a look at my barbershop mirror combination demo. And I'm not gonna set this up as a problem. Instead, we're just gonna qualitatively go through the description of how this demo works. And as I do, we're gonna kind of hit upon a basic strategy, Sean, that is necessary to understand how mirror combinations work. Like a little bit on where we briefly treat a little bit about what happens with telescopes. Now in the case of the barbershop mirror combination, it's just two plane mirrors facing each other and they're parallel to each other. So it just looks like this. Here's mirror number 1, we'll say. Here's mirror number 2. And then just to keep it really easy, let's say that we have a point object right here, exactly halfway in between the two mirrors. And now I'm not going to draw the light rays here, because if I did, it would get really confusing really fast. But instead, qualitatively, let's just describe what happens. For example, we'll have light coming off of the object and then striking the first mirror and reflecting. So then therefore the image that is formed by this mirror of this object is going to be behind this mirror at the same distance as the object distance. That's of course what I just described a little while ago. So then therefore the image of this object is the same distance behind mirror number 1 as what I'm spacing out here in my fingers. That's like this. So here's the first image. Okay, now pay close attention. The light coming off the object, yes, reflects off this mirror, but then it also reflects off the second mirror like so. And when that light strikes the second mirror, where does it look like it's coming from? It looks like it's coming from back here. So then therefore I now have to think of the image from the first mirror as the object for the second mirror. So then therefore right here is now an object distance. So where does the image of this form in this mirror? The same distance behind this mirror as the spacing here of my fingers. So then therefore the image of this in this mirror forms back here. This is my second image. And now the same thing happens for the other mirror. For example, let's say that we have light coming from the object, striking this mirror, and then reflecting. So where does the image of this object form in this mirror? Well, just behind this mirror at the same distance that the object is from the mirror. So then, therefore, this object on my left side, like so, its image forms right here. But when the light coming from the object reflects off this mirror, it then strikes this mirror over here. Where does that light look like it's coming from? It looks like it's coming from here. So the image in the first mirror, once again, becomes the object for the second mirror. So where does the image now of this object form for this mirror? Well, it forms behind this mirror at the same distance that the object is from the mirror. That's back here. So here you get the second image. And so on and so on and so on as you continuously move out from the mirrors themselves. That's how you start to form an infinite number of images as long as the mirrors are entirely parallel to each other. Now hang on a second. What did you notice, however, about the images themselves in terms of their brightness as you looked further and further out towards infinity? They got darker and darker. The reason for that is actually quite simple. The reason for that is as follows. Remember that all that's happening here is that the light is just going like this. Every time that the light reflects, however, not all of it reflects. Some of it is absorbed by the mirror itself. So with more and more reflections, you have more and more absorption occurring, and then therefore the light gets dimmer and dimmer. So this is why very quickly the images kind of gray out, if you will. It appears to get dimmer and dimmer, because the more and more reflections that occur, the more and more light gets absorbed. The basic rule to kind of follow here is that the image for the first mirror then becomes the object for the second mirror. I know, man. Okay, your question? Okay, so let's just pick one pair, one of the two pairs, if you will, and just understand how it gets constructed. Once you get the basic idea, it's fairly easy, but you gotta follow along carefully. So let's say, for example, that we have light coming off of the object and striking this mirror. Therefore, its image forms right here.
It's also the object of the second.
Wait. However, the light that reflects off this mirror to form that image, well, it then strikes the second mirror. So then therefore, it's like, according to this mirror, where did that light come from? It came from back here.
Right.
So that's why I now have to think of this as the object for the second mirror. And then therefore, the image of this in the second mirror is this, right here. But then it also happens with the other mirror. For example, if you have light coming from the object and reflecting off of this mirror, like so, it forms its image here. However, when the light reflects off this mirror and then strikes the second one, now I'm calling this one the second one in this context, that light looks like it's coming from back here. So then therefore, this has to then be the object for the second mirror.
So mirror one becomes mirror two.
So don't pay so much attention to these numbers, just listen in terms of first and second. That's the easiest way of thinking of it. So once again, if you have light going like so and reflecting off of this mirror, it forms an image here. But when the light reflects and hits this mirror, the light that hits that mirror looks like it's coming from back here. So then therefore that has to be thought of as the object then for this mirror, forming its image back here. But then the same thing happens for the other mirror. You have light coming from the object and hitting this mirror, forms this image, it reflects, hits that mirror, that light looks like it's coming from here, however, therefore this now becomes thought of as the object for this mirror, and then therefore it forms an image here. And then so on and so on and so on as you go out towards infinity. You just kind of have to follow the process here as you go. Yes.
I see you're kind of using your fingers to show like the object.
Mhm.
the person is-
Yeah, rather than drawing the light rays, which is all just bouncing back and forth and gets really crowded really fast.
Got it. So the distances don't really matter.
Yeah, they do, they do. I'm just making everything here symmetrical. I'm putting the object exactly halfway in between the two mirrors, so I just stick my finger, you know, right here. And then we're looking at the images that form the mirrors. I'm just thinking of it like that. This is the easiest way to picture it. Okay?
But we just have to know that the second image is further away from the
The way that this goes the same way for telescopes later, is that the image that is formed by the first mirror, its light, when it strikes the second mirror, has to be thought of as coming from that point. That's why we think of the image then, so the first mirror as being the object of the second mirror. That's how mirror combinations work. This is the basic rule that's used in constructing telescopes, for example. We'll get to that a little later. Okay, suffice it to say, however, that's the plane mirror. Next, we get to the concave mirror. Now, you saw a concave mirror demonstration, if you remember, last time in class when we first walked in. I'm going to be kind of slowly working my way towards how that demo works, developing the math as we go. When I eventually do get to the math, what you actually end up with is just one single equation that describes anything associated with mirrors. That's what I'm going to be working towards as we begin this description here. Okay, now with the concave mirror, the mirrored surface is on the inside of the curvature. So here's then how we begin to draw this out. Okay, first of all, right here is the mirror itself. The mirrored surface is on the inside of the curvature. Okay, then we always draw an axis like so that passes down through the center of the mirror, forming a right angle here. This is referred to as optical, sometimes called the principal axis. It's the same thing. Ryan, stay with me. Okay, now we want to understand how images get constructed. We start with the easiest possible situation, eventually working towards our understanding of how my demo involving the light bulb worked from last time. The easiest possible situation would be to form the image of a point object at infinity. Now, if you just think very simply in terms of astronomical terms, what would be an example of a point object at infinity? A star. That's right. So let's form the image of a star using this concave mirror. Now the easiest way to understand what I'm about to do here is to first of all picture a point object close to the mirror, a finite distance away. So imagine that I have a point object here. And now let's just say, arbitrarily, I have 3 light rays coming off of it. Let's say that I have a light ray like so that will eventually strike this portion of the mirror. And then symmetrically above and below, let's say that I have a light ray here, which will strike this portion of the mirror, and then a light ray here, which will strike this portion of the mirror. Watch what happens to the direction of these 3 diverging light rays if I take the object and move it further from the mirror. So now let's say that the object is here. I'm going to draw the same 3 light rays that are pointing towards 1, 2, 3, those 3 points on the mirror. Now the first one, once again, just points like so, towards this point here. Watch what happens with the other 2. This guy points like that, and this guy points like that. Notice that these light rays are not diverging quite so much as they were a moment ago when the object was closer to the mirror. What this means is that if I take the point object, a star for example, and move it further and further away from the mirror, these light rays become less and less divergent. They become more and more parallel to each other. And in fact, if the point object is infinitely far away, then all the light rays coming from it are parallel to each other and parallel to the optical axis. You end up with something that then therefore looks like this. Let me just right away so, becoming more parallel. Guys, optics is easy, you just gotta stay with it. Okay, now, for this diagram, we typically draw just 3 light rays. We always draw the 3 light rays, however, symmetrical. They're parallel to each other, parallel to the optical axis. The first one is very easy. We just draw it upon the axis itself, like so, and then symmetrically above, below, we draw 2 more. And now each one of these light rays, when it strikes the concave mirror, just undergoes the law of reflection. Now be a little bit careful. With this light ray here that strikes the mirror right here at this location, the center, and remember this is a right angle, like so. Be careful, what is the angle of incidence for that light ray? It's 0 degrees, it's not 90 degrees, it's 0 degrees. Because the axis itself is the normal line right here at this location. So if the angle of incidence is 0, then therefore the angle of reflection is 0, and this light ray just reflects upon itself. Okay, now take a look at what happens for the top light ray. Right here at this location, This right here is the dotted line that is perpendicular to the surface. So right here is the angle of incidence. And then from the law of reflection, you just reflect it at the same angle. That then looks like this. Go. So right here is the angle of reflection. Now we do the exact same thing with the bottom light ray. With the bottom light ray, right here at this location, this right here is my dotted line that is perpendicular to the surface. So then therefore, right here is my angle of incidence. And then all that I do is reflect it at the same angle. And what I do, here. Like so. Notice that all three of my reflections, 1, 2, 3, meet right here. That's where the image forms. The image of the star forms in front of the mirror. This is a different type of image, however, than what you've normally seen. Like in a plane mirror, the image forms behind the mirror. That's called a virtual image. In this case, the image forms in front of the mirror where the reflected light rays actually pass through it. For this reason, this type of image is called a real image. This is an example of a real image. Now there is one of these types of mirrors at the bottom of every reflecting telescope. This is the primary mirror. The primary mirror is a parabolic concave mirror. For every light ray coming from the star in this direction and striking the mirror, all of those light rays reflect through this point. This is then where you would see a well-defined, crisp image of the star. Now, in the context of parabola, and especially for those of you who know a little bit about photography, what is this point? Oh, this is the focus, that's right.
Yes.
So, at the base of every reflecting telescope is a parabolic concave mirror. Okay, now, this mirror over here, we would never put this in a telescope. This is a crappy mirror. The reason why this is a crappy mirror is because it's not a parabolic concave mirror. It's instead a spherical concave mirror. Spherical concave mirrors have errors associated with them. The error is referred to as spherical aberration. You can see the spherical aberration in this mirror very easily. Shane, just go ahead and find the best one. Thank you. First of all, take a look at the images that you see very close to the center of the mirror. You see well-defined, crisp images. Nothing looks distorted. However, if you move away from the center towards the edge of the mirror, now you start to see curved lines associated with the images. You're starting to see the spherical aberration. Parabolic concave mirrors do not do this. Parabolic concave mirrors give you perfect images even at the edge of the mirror itself. The reason why spherical aberration occurs is for the following reason. You'll see why with my last diagram. As I said, with the spherical concave mirror, there's an error called spherical aberration.
Sorry.
The spherical aberration works in the following way. Once again, the easiest way to picture it is to find the image of a point object at infinity. But when I draw my three light rays now, I'm going to draw them asymmetrical. I'm going to draw it like this. And once again, first of all, we kind of picture the mirror like so. And now it's not a parabola, it's a sphere. And right here is our optical axis. Okay, now our first two light rays, I'm going to draw basically identical to what I did for the parabolic concave mirror a few minutes ago. First of all, light ray here along the axis like so, reflects upon itself like so. Okay, then light ray here above the axis like so, reflects down like this. Okay, now it immediately starts to look like I'm drawing the exact same diagram as I did a few minutes ago. If I drew my third light ray down here symmetrical to the first, then yes, it would reflect through this point. But if I draw asymmetrically my third light ray down here close to the edge of the mirror like so, when this light ray reflects, it doesn't quite reflect back through this point. Instead, it misses. It basically does the following. Like so. So the three light rays miss each other a little bit. So then therefore, will you see a nice, well-defined, crisp image of the star? No, it'll be fuzzy. It'll look like it's out of focus, and there's no way to focus it because of the spherical aberration. However, the spherical aberration is safe to ignore if the size of the mirror is small compared to the radius of curvature. You can actually see that here in this spherical mirror. Notice that kind of close to the center of the mirror, the images look okay. It's just kind of at the edge of the mirror, like on this diagram, and you're starting to see the aberration. If the size of the mirror itself, just picture it now like this, is small compared to the radius of curvature of the mirror, which is kind of like about this distance here, then spherical aberration is safe to ignore. The reason why I'm mentioning this is twofold. Okay, number one, the math of spheres is easier to handle than the math of parabolas. So we're going to simplify the math here by making that assumption. And number two, girls, how many of you in your purses right now have a compact makeup mirror? Or perhaps boys too, for that matter. Anybody? Well, a compact makeup mirror is not a parabolic concave mirror. It's not necessary to make a parabolic concave mirror for your makeup mirror. Instead, it's a spherical concave mirror. But it's compact. It's small. In other words, the size of the mirror is small compared to its radius of curvature, so then therefore you don't see any spherical aberration for that reason. By the way, notice that if you are close to the mirror, as my hand is right now, you see a magnified upright virtual image. Why that works we'll get to a little bit later on. When you're far from the mirror, you see an upside down real image in front of the mirror. Once again, we'll get to that a little bit later on. But a compact makeup mirror is a concave mirror, but it's spherical. We don't have to bother with parabolas when talking about something that's just used for makeup. The mirror itself is compact. Compact for a reason, so we could ignore the spherical aberration. Yes?
Does the image become upside down on a parabolic mirror as well?
Yes. Yeah, definitely. Absolutely. Okay? But when it comes to the math, we're just going to deal with spheres and not parabolas, and we'll ignore the spherical aberration. Yeah.
So this same type of mirror is also used in binoculars? Or?
No, binoculars use lenses, not mirrors. Binoculars are another example of a telescope. It's what's referred to, however, as a refracting telescope. In a reflecting telescope, you use a mirror combination. In a refracting telescope, you use a lens combination. Lenses involves refractions, whereas mirrors involve reflections. As we'll see, there's lots of similarities, however, between the two.
But that's because of the distance or something that the light has?
No, there are different advantages to each design. I'll mention those as we get further along. Okay? But for now, let me summarize this portion here of today's lecture in the following way. Spherical aberration. Oops, there's two R's, not two B's. There we go. Spherical aberration is safe to ignore if the size of the mirror is small compared to the radius of curvature. So we'll ignore the spherical aberration. Mathematically, however, spherical mirrors are just a little bit easier than parabolics. Spherical mirrors are a little easier. Parabolic mirrors. So that's why I'm bothering to mention all of this. And also, as I said, that mirror over there is definitely not a parabolic concave mirror, it's a spherical concave mirror. And the math is easy for spheres. At the bottom of all reflecting telescopes, regardless of how large they may be, the primary mirror is a parabolic concave mirror. Okay, now, lastly for today, once again starting to show image construction, leading towards our demonstration involving the light bulb, and then eventually the math behind mirrors. The last situation that I'll treat today is to take a look at an extended object at infinity. In other words, an object that's infinitely far away, but it has size, like so, in the sky, for example. If you just think about it in the context of astronomy, what would be an example of an extended object at infinity? Not a star, which is a point. Instead, what else? Planet. What else? The sun. Moon, galaxy, nebula, etc. Something that has an extent, an extended size in the sky, but it's infinitely far away. Now extended. Once again, we're starting to work towards understanding why the light bulb demo works the way it does. This one is a little tricky to draw. It goes like this. All right, now, this is no longer a parabola, it's a sphere, but from this point forward, we ignore spherical aberration. When you're talking about an extended object, once again, think of the object as an arrow. We always position the arrow the following way. We always position the arrow such that the base of the arrow is on the optical axis. And then what we do is we just look at light rays coming off the tip of the arrow and then striking the mirror. Now when these light rays come off the tip of the arrow and strike the mirror, if I move the arrow further and further away from the mirror, eventually to infinity, the light rays coming off the tip of the arrow become more and more parallel to each other. However, relative to the optical axis, those parallel light rays are all on an angle when they strike the mirror. This then gives you the following diagram. Now when we draw this, by the way, we have to choose our 3 light rays here very carefully. The first light ray that we choose is always one that goes like so, down towards the exact center of the mirror. You'll see why in just a few moments when I reflect it. And then symmetrically above and below, we have our other 2. We have, say, this one right here, and then symmetrically below, this one right here. Now, each one of these light rays here undergoes the law of reflection. Once again, all these light rays are coming from the tip of the arrow, which is infinitely far away. Now, the reason why I bother to draw this one right here in the middle, such that it strikes the mirror, is because you can literally see then right here the angle of reflection, or excuse me, the angle of incidence. There it is. And then all that I do is just reflect it at the same angle, and then looks like this. Okay, now the top light ray is also pretty easy to deal with, because right here at this location, this dotted line right here is perpendicular to the mirror. This then shows right here the angle of incidence. And now all that I do is just reflect it at the same angle. When I reflect it at the same angle, it looks like this. So, now notice the 2 reflections that I've done thus far. They meet right there. So when I reflect this last right light ray here, it almost kind of reflects almost on top of itself. Its reflection passes through this point as well to ultimately form the image. It's usually the bottom light ray that is the trickiest one to draw. The reason why it's so tricky to draw is because if right here is my dotted line that's perpendicular to the surface, I've got this little tiny angle of incidence right there. And I then have to reflect it at the exact same angle. But what I do, because I know how this has to work ahead of time, that light ray has to reflect through this pintle here as well, where the other two did. So then therefore, this guy down here reflects like this. And then right here is where the image of the tip of the arrow forms. Notice its orientation. Remember that the arrow was originally positioned like this, where the base of the arrow is just on the optical axis. Therefore, the image of the tip of the arrow is inverted. It's upside down. And then if I did this for all points along the arrow itself, the image of the arrow is constructed then right here. It's still a real image, but it's upside down. It's inverted, as we say. You end up with a real inverted image. Where right here is the focus, once again from earlier, and then this plane where the image forms, those of you once again into photography, is called the focal plane. So, now this is not quite the light bulb demonstration, but it's getting pretty close to it. Because if you recall from last time, remember how I set up that demo? I had the light bulb hanging upside down on the box. Its image form then inverted right side up on top of the box in front of the mirror. That's what I'm starting to describe right here with this last diagram. But if you've ever looked through a telescope before at the moon, and I know that some of you have because I've shown it to you, every now and then a student will ask me, why is the moon upside down? That's why. Okay. All right. Let's take a look here at the board. This is where everybody else stopped. I'm going to stop here today. And I want everybody to fall asleep. Okay, let's go ahead and take a look here at the board. I put out a note on Schoology this morning, by the way, that you may have noticed. I kind of cut the WebAssign in half. I only have a small piece of it due on Friday, and that's the section on chapter 34, which is just Young's experiment. We haven't gotten yet to the math behind mirrors, which, as you'll see at the beginning of class next time, is not particularly difficult, but it's necessary to be able to do the website properly. So then therefore to chapter 32 WebAssign, I've only held off until next week. Let me turn this on.